Hi and welcome to our webinar. This is the second in a series of webinars that we're running on foam fractionation in the PFAS remediation space. I'm Connor Walsh, I'm the CEO of OPEC Systems. I'm joined today on the couch by Peter Murphy, the Managing Director, and David Burns, the Chief Scientist from OPEC Systems.
Hi everybody.
Fantastic turnout for this second webinar. We've had sort of over 200 registered people, registered attendees, coming from all facets of the PFAS world. So that's very encouraging. If you missed the first webinar, it's available on our website at opecsystems.com. We'll give you a little rehash of it a bit later on today, but it's certainly there up and loaded for you to watch. We'll be answering questions at the end of this webinar, so we really encourage you to, in the bottom right-hand corner of your screen, there's a chat box. Really encourage you to go and log some of those questions there, and at the end of the webinar, we'll come back and answer those questions for you. So we've got all day as far as we're concerned, so please ask as many questions as you can, and we'll stay and answer those. Just an overview of what we're going to cover today. We're going to have a look at an introduction to the Australian Aviation, Army Aviation Base Oakey water treatment plant that we've got up there. And we're going to look at SAFF, Surface Active Foam Fractionation. So we'll look at that as a concept and explain that in a bit more detail. We'll look at what the objectives were when we set up the water treatment plant at Oakey. And then we're going to go and visit Oakey several times. We'll go back and forth. And answer questions about specific stages in that water treatment plant. We'll look at some of the safety aspects of that water treatment plant and also some of the value add of putting that treatment plant up in Oakey. And then we'll go to questions and answers. So Pete, before we just recap on the webinar, I am quite pleased to see that since the last webinar, OPEC Systems was awarded the Defence Innovator of the Year at the Australian Defence Industry Awards.
Yeah, it's great.
2019. It was a pretty big achievement, really.
Yeah, it was a big award made up against some really stiff competition, and we were lucky enough as a small business, small medium enterprise to get the award. But we focused on two areas. One was for the SAFF work that we'd done with Defence at Oakey, and the other was for the chemical suits that we're supplying for the next 10 years. So it was a really good outcome.
It was very exciting. Yeah, unfortunately, I was on holidays when the dinner was there and missed the presentation. But very exciting. So Pete, can you just give us a quick recap of some of the things we covered off in webinar 1?
Sure. Yep. So webinar 1, we really wanted to give the audience a bit of an overview of foam fractionation. So going back 4 years when we started on the PFAS journey, we looked at a range of different technologies for PFAS remediation, and a sort of poor cousin emerged called foam fractionation. That was the use of air bubbles effectively to float PFAS contamination out of contaminated waters. And as that process evolved over the first year or two, foam fractionator kind of rose to the top as the primary treatment technique, and since then we've just focused on foam fractionation. So webinar 1 really looked at that journey, took people down to the treatability lab where we conduct our treatability tests for our clients to determine what the right treatment train is for their particular problem. And then we also had a little bit of a look at how we've scaled up and stepped up that PFAS remediation capability from that very early lab stages right through to the full scale plant
so
we've
what
got
we're going
now.
to see today. Yeah, I do remember that probably the first test was covered in a small beaker, and then
tiny little 1 litre bute in a flask, and then a 10 litre fractionator. Yeah. But I mean, if people want to go to OPEC's website, www.opecsystems.com, you can jump in there and have a look at that first webinar.
Excellent. All right. Well, Dave, I want to come to you. Just give us an introduction of SAFF.
Okay. Well, SAFF is basically surface active foam fractionation, or SAFF, is the lead treatment in OPEC Systems water treatment plant process, so a multi-stage water treatment plant process. And SAFF is a modified form of foam fractionation that applies the principles of green chemistry to rapidly separate and concentrate PFAS from water to below the Australian Drinking Water Guidelines in a single step. And that's really the main point and the power of SAFF. But SAFF also reduces other high Henry's constant compounds or co-contaminants and non-fluorinated foaming agents without creating secondary waste. And as we've found out that if you don't have secondary waste being created, you don't need regen. So it's been a great technique that we've invented.
So yeah, I like the single step. It did remind me of that other famous one small step for PFAS remediation. Dave, can I ask you then, just can you just outline some of the key objectives that we were set when we were designing the water treatment plant for the Army Aviation Base at Oakey in Queensland?
Yeah. So I guess to frame it up first, that the project, we needed to address hydrocarbons or potential for hydrocarbons and PFAS. So the objectives, number one, was to find a sustainable solution capable of removing 100% of the criteria compounds, which for us were PFAS, PFHXS and PFOA, and also to align to the ITRC's remediation theme of separation, concentration and destruction. So that was a pretty important objective. The second objective was to manage cost. And I guess SAFF in its most basic form is a rainwater tank with a variable speed pump and venturis to aerate water. And as we all know, air is still free.
Yeah.
So this translates into our key message of air in, PFAS out, and this helps keep costs down.
So just let's explore the chartered accountant in me likes to explore costs. So really, on a plant like this, we've got two costs: the capex and then the ongoing operational costs. So just delve a little bit deeper into the capex side. And
well, again, this comes to that key point of SAFF being a combined separation and concentration process. So this means that the capex and the opex remain fixed regardless of the concentration of PFAS that we're remediating. And essentially what that means is that SAFF does the heaviest lifting at no extra cost if applied to the source zone, where you remove the most molecules of PFAS.
And I guess to sort of explain the difference there, if you've got resins or carbons, you've got a certain amount of active sites that can absorb a certain amount of PFAS compounds. And so the higher the concentration, the faster those beds are going to become saturated. The difference with SAFF is that it's a physical separation step, so it operates irrespective of concentration. And so we sort of advocate to our clients, take us to the kind of dirtiest, mankiest corner of the site where your PFAS concentrations are highest, typically adjacent to your source zones, and then we can really do the biggest heavy lifting there to remove all of those criteria compounds and a bunch of other compounds while we're at it. And the cost doesn't change. And so, it doesn't change. And similarly with the OPEX, it doesn't actually go up. There's no additional consumables. There's no higher levels of wastes over time. So you actually got this very steady commercial model.
Right. So coming back then on the objectives. So
another objective was managing waste streams. And the waste stream for SAFF is remarkably low, because we're removing PFAS by aeration and then concentrating it into a very, very low volume. And I might say that this is also quite desirable by the third-party destruction cell developers that are interested in testing that low volume, high concentration foamate waste.
Yeah, this is a really fundamental difference maybe for the audience who aren't familiar with physical separation strategies. So rather than absorbing it in a medium of some description, we float it out as a really concentrated foam. So to give you a quick idea, on Oakey we do 250,000 litres a day, and at the end of each day we end up with about 3.5 litres.
There was a graph from the first webinar which I thought was really useful and might be worth just coming back to. So it's blue on one side, which is the water, and as we move through that process, the water's getting clearer and clearer and clearer, so the bluer it gets.
Yep.
And then on the other side, we've got the PFAS concentrate getting...
Stepping up in concentration.
Yeah,
through
so
each
maybe
step.
just talk us through that.
A lot to take in. So, but effectively, we've got 4 separation steps, which we take you through in the video in a minute. But at each concentration step, we get a 20 to 30 times concentration of the PFAS contaminant on the one side, and then the water that's treated in that particular step is then cleaned and polished. And so by the time you get to the 4th stage, we've elevated where we're up around 2.5 million parts per billion PFAS concentrate, like a slurry.
Yep.
That then lends itself to the defluorination and other destruction techniques that we've been working on. So what we're aiming for is a complete closed loop on-site destruction capability.
Right. And I seem to recall from Oakey, it was 250,000 litres a day, and then we were left with a sort of highly concentrated
3.5 litres.
3.5 litres, which is pretty phenomenal, because over a year that's
a bulky in a year one, intermediate bulk 1,000 litre container, about 250 gallons.
And then
So in effect, what we're trying to do is reverse using the concentrate that the firefighters use to mix into water to put out a fire.
Yep.
We're trying to put that process in reverse, so taking dilute PFAS and putting it back into that AFFF product bottle.
Yeah, except we're not going to resell it. Okay?
No.
We're definitely going to dispose of it. So any more objectives on?
The 4th objective was, I guess, to optimise any polishing technique that we wanted to use. So what this meant was that SAFF became the lead treatment in our treatment process because it conserves the polishing or the expensive polishing techniques which we use as a fail-safe stage, and also to remove those bloody annoying short chains.
I mean, I just got back last month from the CERTA PSTCP conference, and one of the interesting things I realised at that conference was that there is typically a combination of GACs and resins to do the work of polishing PFAS contaminated water at the moment, and the GAC is very much seen as removing the long chain elements, and the resins are seen as polishing the short chains out. And I guess in many ways we're kind of to some extent replacing both of those. We're certainly replacing the GAC. We don't have any GAC in our plant other than for filtering some of the air on the plant. Yep. But all of the long chains are lifted out. 100% of the long chains are lifted out through the fractionation process, and about 86% of total PFAS is taken out by the fractionation process, and then that tiny little residue that's remaining is then put through the ion exchange resins for polishing, and we go into a bit more detail on that on the video.
I like it. A lot of the catch or the word that I've heard is it's the heavy lifter of the heavy water treatment plant, which I kind of like. And Dave, there's one more objective, I think.
So the final objective was good design, and the good design allows foam fractionation to be derived into other engineering applications for in situ, ex situ, groundwater, surface water, trade waste and soil washing applications. So that's basically been the approach up at Oakey, and now we're looking for further improvements to make delving into ultra trace remediation and get better at the short chains.
Yeah, it's probably for a lot of the guys in the US who don't know us, OPEC as an Australian-based company, we're an environmental engineering contractor, so we have a lot of draftsmen and engineers, electrical, mechanical, and like designing and building stuff is what we do. And so we have been sort of taking these designs. We have a very good ability to go from concept through design through to commercial scale operation in a short period of time. We've got 8 workshops. We can pump that stuff out pretty quickly.
Yeah, I mean, I have to say I'm pretty proud of some of the engineering feats that we have delivered over the years. So that's a pretty good segue, because we're going to go up and have a look at some of the design elements of the Oakey water treatment plant. So we're going to go and have a look at the first stage we're going to look at is the pre-treatments, which is stages 1 through to 6. But just before we go up to Oakey, it's probably worth just giving our viewers a bit of a concept of where Oakey is and the extent of the problem up there. So now just bear in mind, these slides we're showing you now are publicly available and have been approved from Defence and AECOM for us to show today in this webinar.
Yeah, so mate, that's just a good aerial view of the Oakey site. So Oakey is really just a large village in southeast Queensland. It's the plume you see there is probably about 6 kilometres long. In the top right corner, you can see the aviation base and the perimeter of that. And what you see is there's been a slow movement over the last 20, 30 years of that PFAS plume under the village itself, which obviously is cause for concern for the local community, and Defence have been working quite hard on that site to manage this problem. And then if we drill into the next slide, you can see that there's basically 4 ways that groundwater's leaving the site.
Surface water.
Surface water's leaving the site, thanks Dave. And then that you can see the different coloured drainage channels there. And you can also, there are the key hotspots on the site are also illustrated on that.
So our plant, from memory, is by the pink channel. Is that right?
So we're just up near the top right of that pink channel is where we've located the OPEC plant, and so we're quite close to the one of the original fire training areas on that site.
All right. Well, without further ado, let's jump up to Oakey and have a step through those first 6 stages.
Okay.
Hi guys, here we are. We've made it up to Oakey, just west of Brisbane, about 3 hours up in Queensland, and we're here at the OPEC PFAS water treatment plant. So it's a project we've been working on for really 4 years in the making, I guess, to get us where we are. We've started building about 6 months ago. It took us about 3 months to get the unit up and running, and we've been in commissioning phase getting it ready. So I'm joined today with Mr. Steve Phillips. Steve's one of the co-inventors of foam fractionation, and he's also been the driving force behind both developing the technology and getting it to a commercial stage here on site. So the Oakey plant is a 250,000 litre a day treatment plant for treating PFAS contaminated water. It's one of only 3 treatment plants that we're aware of in the country, and certainly in the world stage for PFAS treatment it's quite unique in terms of being a commercial full-scale plant. So we're going to run through a few things on the plant today to try and give you guys some education on how it works and what we've achieved. First stage we'll have a look at where we're drawing the water from and what we're treating. Second stage is we're going to run through the pretreatment, so there's a little bit of prepping to get the water ready for fractionation. We'll then run through that fractionation phase itself. We'll then have a look at some of the dewatering and how we manage the waste, and then we'll look at the final polish before we're ready to discharge to the environment. So if you come with us, we'll take you through. Let's go. So we've made our way over to the well array, which is situated adjacent to the fire training area. So with the fire training areas, as probably most of you know, the PFAS used in the firefighting foam makes its way off the apron, along with some other co-contaminants. It makes its way down, migrates vertically through the soil until it intercepts the water table, and that's when the trouble begins. That's what we're trying to deal with here at this hotspot. So we've got an array of 5 wells at the moment that are feeding our system. We're looking to expand that array over time, but Steve, perhaps you could just take us through the individual wells, how they're operating, what they're doing in there.
Yeah, so right behind us we've got a well. In this well we've got a compressed air system which is driving a submersible pump which is about 20 metres down in the well. That submersible pump is taking groundwater from the environs around the well, pumping it up through and down to the water treatment plant. The pump is driven by compressed air, and each pulse of air that goes through the pump pumps about 600 mils up and out. The air and the level of the water inside each well is monitored, and the information is transferred by optic fibre back through to our plant.
So you're controlling each well individually, you can see what the flow rate is, and if you had to, you could just shut the whole system down, is that right?
That's right, yeah.
So that winds us up here at stage 1 at the well array, so we might just head across back to the plant and we'll just start to take you through the finer details. So we've taken a bit of a stroll from the well array, which is about 400 metres to the north up here. We've got the 5 wells over there. We've directed the water over to this pre-treatment area where we get the water ready for the fractionation and subsequent polishing phases. So this really in our plant covers phases 2, 3, 4, 5 and 6. So we might just get a quick run through those, Steve, if you can.
Sure. So what we've got here is we've got the entry of the groundwater into the plant. Sometimes it contains suspended sediments that come out from the soil and the ground around the wells. And so that water comes into this large black 15,000 litre storage tank behind us with a sloping base. And in that tank, a lot of that sediment settles out to the bottom where we can tap it off and take it elsewhere and dispose of it. After it travels through that tank, it comes down through the pipework here into what is called a coalescing plate separator. And this is quite an important part of the plant for reasons which Pete will explain to you right now.
The hydrocarbon issue is quite an important one, and it's one we'll probably come back to a few times through the presentation. The reality is, on these old fire training areas in particular, there's a lot of hydrocarbons get mixed up in the co-contaminants. And so, you know, you're using accelerants, you're using fuels to start fires, you're burning old vehicles. It's very common to have hydrocarbons commingled with your PFAS. So realistically, any system that is going to effectively treat PFAS from groundwater, it has to be able to manage this hydrocarbon problem. So we put quite a lot of effort and time into a number of the phases that deal with removing that contaminant before we get to the resins. And the reason we do that is resins are very vulnerable to hydrocarbons. And so through the various stages, the coalescing plate separator and some of the later treatment phases, we're actually trying to extract both the free phase and dissolved hydrocarbons before they get to the resins. And that really optimises that resins. They're expensive, they generate waste. We want to use as little of them as possible. And so we're very focused on this part of it. The coalescing plate separator, fairly standard piece of industrial equipment, gets our free phase oils out down to sort of 10 to 30 parts per million. So essentially there's no visible oils or fuels on the surface of the water, and then we flick it onto our next stage, which is stage 4.
Yeah, and I might just add there that one of the main reasons we're doing this is right at the back end of the plant we've got some absorbent resins. They're very sensitive to hydrocarbons, so we really got to remove those. But the other thing about this back end of our plant, the resins, is they're sensitive to other materials as well, and there's iron and manganese and other multivalent cations will also clog up our resins and preclude them absorbing PFAS. So we want to get rid of those in this area as well. So in the next stage, what we've got is a large aeration tank here. So the water travels from the oily water separator, moves into this preliminary aeration tank. It's oxygenated, it's aerated, and in that process, the iron and the manganese are oxidised, and then they travel through the plug flow reactor behind the tank into these filtration banks in the 20-foot container next to us.
And this is really just to capture those precipitates that we've managed to get out of solution. And so we've got a series of diminishing bag filters starting at about 25 micron. We run that down to 1 micron. So really a lot of these suspended and solids that come in through the groundwater wells, by the time we get to the end of phase 6 here, we've removed those. We're ready to move across to the fractionator.
Well, welcome back. It's good we're seeing the first stages of the plant. I'd encourage our viewers, if you've got questions just on that pre-treatment stage or any questions, just jump onto the chat box in the bottom right hand corner and log your questions there, and we'll get back to them at the end of this webinar. So guys, we covered a little bit about the need for that pre-treatment, but maybe just go back and headline some of those things.
Sure. So when we were given the particular site that we worked on there at Oakey, it was a dual issue. There was a combination of potential hydrocarbon contamination as well as PFAS contamination. And so, as we kind of allude to in the video, they can potentially be two products that don't mix particularly well. So we had to remove the hydrocarbons before we dealt with the PFAS. And so one of the, if I look at the overall plan and sort of break it up roughly, the pre-treatment stage was about 1/3 of the investment. The fractionation phase that we'll go to in a minute was another 1/3, and then the resin phase was another 1/3. But the pre-treatment and the resin stages wouldn't have been as necessary or wouldn't have been as complicated if we hadn't have had the types of contaminants we've got on site. So part of that process of assessing individual sites for their particular water chemistry, their lithology, the type of co-contaminants you're dealing with. That's why we have the treatability lab. That's why we think it's important to do a lot of characterisation of that water before we actually build a plant, because sites differ.
Changes. Yeah. Okay. Dave, anything to add on that?
You pretty much covered that there.
Pretty much covered it nicely there. So, and I'll come back to that later when we've gone and had a look at the fractionator of just looking. We'll look at just how much that can lift out of the PFAS side of things without the need for and polishing. But why don't we go up and have a look at the fractionator, and then we'll come back and cover that in more detail. So we're going to jump back up to Oakey and look at stages 7 through to 11. Which is what we call the heavy lifter of the water treatment plant.
That's it. This is the good bit.
We're finally at what we think is a really interesting part of the plant, because we invented it, so we really like it. But this is the foam fractionation phase of the water treatment. So foam fractionation of PFAS is a process that we developed and patented, as we said, over the last 4 years. Lots of hard work gone into it, and ultimately culminated in these units that you see behind you, which is stages 7 and 8 of the water treatment process. So, Steve, give us a bit of a rundown. These are your babies.
Here behind me we've got 5 large black vessels. Within each of these vessels, 2,000 litres of water is processed over a 50-minute period, and in that time it takes the PFAS and strips it out of the water, and then that strip with that water that's driven off through the top of the fractionator goes to the following stage of the plant, with the treated water going through to the polishing end of the plant.
Yeah. So this stage is really interesting. It's a bit like if you imagine the pistons on a motor. We're sort of driving through 2,000 litre batches every 50 minutes, which is what's allowing us to achieve our 250,000 litre a day capacity. And we should say that that's based on a 50-minute processing time. And we're looking to reduce that significantly, maybe as low as 20 minutes, which obviously is going to enhance our overall capability.
And one of the important things about this process is there's nothing else added except air. So we've got this little motto that we've coined: air in, PFAS out.
And it's unique. It's the thing that actually separates us. So there's a lot of activated carbon plants and some really good resin plants, and while those products work really well, the mechanical, physical separation phase is what makes this really unique. So we're pulling out the PFAS as a hyper-concentrated foam. So to give an indication of that, we start with 20 parts per billion coming out of the wells. We finish our final stage at 2.5 million parts per billion. So the concentration steps throughout this process are enormous. This is the first of the concentration steps. It steps us up about a factor of 20
to 30 times.
20 to 30 times through the thing. So let's jump over. We'll have a look at the hyper concentrator, which makes up the next stage and is another concentration step, bringing it up about another 30 times again.
Yeah. Well, here we are at stage 8, which is what we've termed the hyper concentrator, and that's the tank that's standing here right behind me. It's about 1,200 litres. It's currently operating in batch mode, and you can see up the top of the hyper concentrator we've got a whole lot of water and foam swirling around, and it's in the hood where the action's happening, and you can see the foam being extracted by vacuum in the top.
This is probably for us one of the more exciting bits. This is where the patent and where the innovation lies. What we've managed to do is take this process of essentially air in and PFAS out, bubbles into water, and introduce with the right veracity, the right bubble size, the right sort of dynamics inside the vessel, and the right type of vacuum system, we're able to really efficiently harvest that foam out. So if you think in stage 7, we took a 20-time concentration step. Here we are at stage 8, so we've gone from 20 to about 400 to about 20,000 parts per billion at this particular water chemistry. So it's a fantastic step up. All of that before we've introduced any chemicals. It's all just a physical separation process. And so the hyper-concentrate we produce, we're then able to store and take onto our dewatering phase and produce a really minimal amount of waste. So let's jump up, have a look.
So although we're already about 10 or 15 minutes through this particular batch, you can see that the foam that's coming off right at the top there, it's a lot stronger than it was in the previous stage.
Yeah, so we're applying a constant vacuum onto this head, and then that's running down to a knockout drum in the next container where we're going to go in a minute, and then we'll see how we take that from there, dewater it even further, so we're getting absolute waste minimisation out of the original source water. We're really, we've treated already, you know, in a given day, 249,000 litres goes through the system for initial treatment, and then it's polished. Then this system, the last couple of 100 litres, we're able to reduce that down to what is ultimately about 3.5 litres of waste per day.
And the 1,100 or so litres of water that's been fractionated in this vessel, it's almost to drinking water standards, but what we do is we take it and push it back through the system again.
Just as a precautionary thing, just in case. So the safety's quite important in this phase. We really need to manage the PFAS hyperconcentrate, and so we're starting to move towards dual skin pipes. We're starting to move towards minimising how far we travel it in the system, and we just bring it into the container right next door to this one, where we're going to move to now and just have a look at how that's done. Okay, so next stages, I should say, 9, 10 and 11. So this is all about dewatering. This is all about taking that really beautiful hyperconcentrate that we've managed to get off the foam fractionation phases and then taking the water out of it. So effectively we've got a few stages, mate. What comes first?
So right in the back end of this plant, we've got a holding drum where all the water's come out of the back end of stage 8. That's pulled through into a vacuum distillation unit, and it's there that that fluid is put under a very low pressure, and it's boiled off. The water is boiled off from the in a pressure chamber.
Yeah, at about 60 degrees we're doing that, bit over. And so what we get in that step is we get about 97% of the water comes out of that particular solution that we put in there. So here we go, third concentration step, another 30-fold. We're going from 20,000 parts per billion up to 600,000 or 700,000 parts per billion. So you can see we're really starting to get down to the business end here. And then we move on, final stage.
And the final stage is a drying unit, and this solution that we've gathered is starting to get a little bit viscous, and so we put it inside the drying unit and we dry it right out till it forms a sludge-like product. And one of the big advantages in this process is we're reducing the volume and weight of the material that is a waste product, and so we're saving clients a lot of money in the disposal process.
So this last step, about another 30-fold concentration step, takes our final concentration up to around the 2.5 million parts per billion. So after treating 250,000 litres in a given day, we're now looking at about 3.5 litres of highly concentrated PFAS waste mixed up with a little bit of other bits and pieces along the way. But at about $5,000 to $8,000 per tonne to dispose of this waste, you can immediately see the advantages of this hyperconcentration process. It's fantastic. And so, and also all of that rich PFAS, now out at sort of 85%, 90% of what we were originally dealt with at the source water, is just here in the concentrate. We haven't had to put it through resins yet. We haven't even got to that stage. That's the next stage. So we'll go for a wander over there and we'll just show you this next and final stage of the process.
So back here, getting a better understanding of just how that water treatment plant it fits together. Again, I just encourage our viewers, if you've got questions, ask them, bottom right-hand corner in the chat box there. We're getting a couple of questions coming through. Christine, you're certainly active on the questions, which is good. I'll come back to most of those at the end of the webinar, but I will just answer one of Christine's questions, the first one here. Just, do you have to remove metals before that fractionation process?
You don't have to remove metals per se for the fractionation process, Christine. I mean, the fractionator vessel itself is enormously robust. We can take a lot of cross-contaminants, including metals and hydrocarbons and just about anything else you can throw at it. In fact, there's probably a picture somewhere of when we were in the early days trialling this system to seeing if we could break fractionation. We put in a whole bunch of suspended and dissolved solids. We played with different levels of oils and different types of contaminants we could put in there, and the fractionation process itself continues to work. The reason why we extract metals is because if they oxidise, so on this particular site we produced a lot of calcium carbonates, and so we were, because they have the potential to blind the resin bed, we wanted to pull those out early, and so we actually take those out pre-fractionation, we take them out again post-fractionation, so we do manage them again. A lot of this work is to preserve our resins and just get the best value out of that phase.
Yeah. And Oakey has hard water, so if we don't pull out the calcium and the magnesium, the pumps and the pipes will tend to scale.
Right. So wear and tear on that, on the equipment. Yeah. So guys, so Christine, there's a bunch of other questions coming through, which is great, which we'll get to at the end of the webinar. I just thought that one was quite relevant for what we'd just covered.
Sure.
Just now we've come away from the fractionator. Am I right in saying at this stage we've removed all the long chain PFAS compounds?
You are correct. So at that stage, 100% of the criteria compounds. So in Australia, as we mentioned, PFOS, PFOA and PFHXS are our criteria compounds. So we've removed 100% of those, as well as a bunch of the precursors and long chains. And by long chains, we mean C6 and above. We're getting all of those out pre-resin, so post-fractionator.
We have some slides, tables that we probably should throw to.
Oh yeah, this is a good one. So the centre column, which is labelled SAFF only there, you can see the PFAS compounds on the far left that we're dealing with. And so you can see just with the SAFF, we've removed a large amount of, so all of the PFOA, the PFOS, the PFHXS, that's all come out. I know in that graph it says 98%. We're actually getting better results over the last month or so of testing. There's a number of other long chains that you'll see, the bottom five there, the PFOSA, PFNA, PFDA and the fluorotelomers there. We're getting those out of solution, and we're getting varying amounts of some of the shorter chains.
So what SAFF's doing there, it's removing the long chain PFAS down to 0.01 microgram per litre, which is 10 nanograms per litre.
I love it. It looks
which is below the Australian drinking water criteria, and in Australia the criteria is just for PFOS, PFHXS and PFOA. In the US, various states have many other compounds that have criteria, and that table shows which ones we are able to effectively remove in the US context and which ones that SAFF would not be able to currently remove. And that's why we demonstrate the Oakey plant using resin.
Yeah.
So the next column over shows that after the resin polish, we do remove all of them to less than 0.01 microgram per litre. And when we test the same water to ultra trace level in the lab, we're actually going down to less than 0.001 microgram per litre, or 1 nanogram.
And again, probably highlights the need for us to look at a client's water down in our treatability lab to just identify what we're going to be dealing with before we design them.
I mean, it's just a good idea. It makes sense to, before you design something, you want to know what you're dealing with.
So if we go to the next slide, there's a graph that shows the speed.
Oh, yeah.
So what this graph, kinetic degradation graph or percent removal graph shows is when the plant is operating, we've got Len, or it might be Rowan, sampling one of the 2,000 litre primary fractionator vessels as it's running, so in batch mode or continuous batch mode. The cycle is about 50 minutes, so he's sampling the bottom of the tank as it's operating every minute into about 30 bottles, and then we send all those off to the lab. Some of them we keep on hold, but we have them tested at various points to work out where the removal rates in time occur. So PFOS and PFOA tend to drop below the drinking water criteria in Australia, around 3 to 4 minutes of aeration. PFHXS around 10 to 12 minutes.
It's pretty phenomenal when you think there's real scope for us to reduce that batch time that's going through, which will ultimately increase the volume of water you can treat there.
And I guess the next step for us is to do some other tasks or modifications to see if we can push the treatment down to even lower concentrations and be more effective at those really low C4, C5 carboxylic acid short chains and rely even less on resin.
Yeah, no, I enjoy that graph. It reminds me of my daughter's uni results, 100%, 100%.
Yes.
Hey, so I think we're going back up to Oakey now just to look at that polishing stage. Again, we've got some great questions coming through, which is good. But we'll go back, we'll have a look at the polishing stage. Keep logging your questions if you're watching this, and then we'll answer those as we come back.
Great, thanks, mate.
Okay, stages 12, 13 and 14 of the OPEC PFAS treatment plant. You can hopefully just see down the back of the vessel there. This is our polishing phase, and in this stage we've got a couple of discrete elements that we work with. So what have we got here, Steve?
So what we've got here is we've got a lead and lag configuration of a couple of vessels which contain different sorts of exchange resins. When the water comes through from the fractionation vessels, it contains a lot of the small chain PFAS compounds, but it also might contain hydrocarbons, dissolved phase hydrocarbons, which has somehow not been removed in the fractionation process. So what we've got to do is we've got to remove those, and that happens in the hydrocarbon absorbent resin, and then the water flows through to a resin that is specifically tailored towards removing PFAS compounds. Now these resins, they're quite expensive. They're quite unique actually. They remind me a little bit of caviar.
Yeah, some selective resins that are really working on those specific contaminants, and we have to really nurture them along. A lot of what you've seen in the previous part is about protecting these resins. They're high cost and they're a waste stream. They're two things that we don't want to blow out for our clients or create for our clients. So this is the final stage. The hydrocarbon resin has a lead lag arrangement. The PFAS resin has a lead lag arrangement. It's just a sort of an extra precautionary approach. In the event that you get some sort of breakthrough or there's some sort of breakdown in the resin materials, we've got a contingency and then contingency on contingency. So by the time the water exits this system behind us, it is sparkling clean, drinking water quality, ready to go back into the environment. And so just before we take that final step, we'll just run over to stage 15 here, which is just where we hold it and store it prior to discharge.
Okay, let's go. Okay, so here we are at stage 15, which is the final stage in the OPEC water treatment plant. And behind me here we've got 5, I think they're about 15,000 litre tanks. And each of these tanks stores the product that comes out of the back end of the polishing process.
So back into stage 14, we've finished all of our treatment. It's gone through the final polishing stages, and we're just storing it here because part of our requirement with the client is just to make sure that we meet the drinking water guidelines. And in fact, our requirements are considerably more stringent than the drinking water guidelines. We're trying to meet about a third of the drinking water guidelines for our treatment process. So we're down around 0.02 parts per billion of total PFAS. So it's quite a stringent standard, but luckily we've been going now for a few months and we haven't once yet failed to meet that guideline. We are just inside the control room where we're going to have a quick look at something that I think is really exciting before we head over to stage 16. So this is where the brains of the operation are, not just Len Brown here, our operations manager, but also the PLC logic system that we've built onto the back of the plant. So the intention was there's a lot of remote sites. We don't know where they're going to be. We don't know how many of these systems will ultimately be out there, but we want to be able to manage them, understand how they're working. And so remote telemetry was a really important aspect of that capability. So we've gone the extra yard on this plant. Every pump, every valve, it's all links back to this particular control centre.
So we've got water in at the top right hand screen. Inventory tells us how much water we've actually got on the plant at any given time. We've got the water discharge visible on the front screen as well, all the stages, and we've got some other reporting characteristics and a whole bunch of data tabs that we can get to, all from the screen itself. So for example, we can look up how much water came in today, how much we've pumped out, what our power consumption is, how many hours each one of those pumps has actually been running for. I don't have to be here to drive this. I can drive this from home by simply logging in, or I could be down in Melbourne or somewhere else in Australia or overseas, log in, and I can see that particular data as well. From here we can isolate all the wells, just push of a button, we can turn them all off, or we can actually go out to the well, turn the individual ones on and off accordingly. Next screen we've got water coming into stage 2, and you can see the transfer from 2 to 3 onto 4. We can see the volumes that are in the tank, all the data's in here necessary for an operator to very easily control the functions that are in here. Now, even though I can control it, the beauty is it's all automated. So unless there's an issue that springs up, such as low air pressure and the valves fail to open, for example, this plant will virtually run itself.
The point here is, through understanding the water in, the water out, the power, the waste produced, we're able to really accurately develop some metrics around the performance of the plant, the cost of the plant. So there's really two things that we're interested in. We're interested in the cost per milligram or gram per mass of PFAS removed from the environment, and the cost per litre of PFAS contaminated water treated. If we can harness those two metrics, we can really do some great comparison between different technologies in different parts of the world and understand the quantum of this problem and what it's going to cost us to resolve. So we've put a lot of work into being able to capture that data, and I think it's now that we're actually generating data on site, we're starting to reap the rewards of that. So, all right, so that was just a little side journey to show you through the brains part. We'll now head out into the bush, as I said, and we'll go and have a look at where that clean water's heading to. We're out in the bush. We're about 300 metres east of the water treatment plant. Behind us you can see some crystal clear water pumping out into the environment. So we're at the end of a very long, circuitous journey. Thanks for your patience. So we've now got this clean water, mate. What are our options?
Yeah, so we've got a few options. The first one that's being adopted here behind us is irrigation. So all the water is being used to irrigate the natural environment. We've also got another option of re-injecting this clean water back into the aquifer where it came from. And the other option we've got is reusing the water for construction purposes. So the water is safe to use, and it can be used for a variety of actions, including dust suppression.
Yeah, that's great. So it's a pretty good news story from our perspective. I'm really proud, mate, of you and the team and everything we've done over the last 4 years to get us here. We're taking 250,000 litres a day of contaminated water, and we're treating it down to drinking water guidelines. We're re-injecting it back into the environment. It's making its way back into the aquifer as crystal clear, clean water. It's a great outcome, mate. Good on you. Thanks very much. No. So that's it. Let's pack up our gear. We'll make our way back to Belrose and carry on.
Good one.
Well, great. That covers off the whole water treatment plant. Just again, if you've got questions, log them in the chat box. I will just come to one question here because I think it's quite relevant at this stage of the webinar. So Amy asked, the 97% of the water that comes out of the hyperconcentrate, does that have PFAS in it?
It does. It doesn't have any long chain PFAS. So you might remember that what we skim off the first reactor vessels then go to a knockout drum where they're taken to the hyperconcentrator. So that water still, even though it doesn't contain the long chains, it still contains some of the short chains. In the hyperconcentrator, we then refoam it, take a concentration step again, as I mentioned there, 30 times or so, and the water in the hyperconcentrator is actually directed back to the front of the plant where it's diluted down and sent back through. It could go straight to the polishing resins in reality, but just as a precautionary measure, we pump it back through. It doesn't actually contain any higher levels of short chains than the original, of long chains than the original fractionated water. But as we're moving towards higher concentrates, we just sort of take in stages 8, 9, 10, 11, we take that water back to the front of the plant, just in case somehow there was a leak or some cross-contamination issues. We when you're dealing in parts per billion and parts per trillion, you've got to be really careful of how you manage the concentrates.
A redundancy in the design.
Yeah, but all the long chains are removed in
To
that
the lab detection limit.
Yeah.
So guys, we filmed that video back in, I think, around May of this year. It's now
May.
October. What have we learnt since that commissioning?
Yeah, it's been a pretty long 5 months, really. I mean, we've learned a lot, and that's the great joy of having a commercial scale plan is the learning that you can do in that sort of environment. It's one thing to have things in a lab or conduct periodic field trials, but when you're banging away 24 hours a day, day after day, you really do learn some great lessons. So, from an engineering perspective, we've learned a lot. We've shifted things around. We've included things. We've added water softeners. We've added pH adjustment. We've looked at issues around temperature. We've changed our bag filter configurations to take precipitates out post fractionation as well as pre-fractionation. We've introduced variable speed drive pumps because we found we were getting a bit of hammering. That was actually a big issue for us. We, instead of in those reactor vessels in stage 7, we were topping up with processed water. We now top up with potable water because we found we got a bit of cross-contamination at that phase. And lots of small and large changes have occurred. And so we've been seeing this progressive improvement in performance to the point now where, I mean, we're frankly amazed at just how well it's working.
It's one of our core values. Good today, better tomorrow.
That's it.
So.
Yeah. I guess there's like some value adds that have occurred.
Yeah, so just tell us about some of those value adds at that Oakey site.
So one of the value adds has been that not only does the plant operate to remediate groundwater that's contaminated with PFAS, but site civil works where there's runways being renewed or there's construction works to build new control towers. Sometimes, like when it rains, there might be an excavation that fills with water. That water has to be treated. So the civil works guys on site now bring water to the plant. We have 2 50,000 litre tanks that we receive water.
You've got an image of that.
And we put it through the plant, and then we have a third and a fourth 50,000 litre tank, which we fill with treated water. And the same civil guys come and connect up with their water cartage trucks for dust suppression water. And what that does, that saves them driving into town, getting potable water that's valuable for drinking purposes during drought.
Yeah.
And conserves water.
Particularly in Australia. Actually, I just see there's a question comes through from Clint, which is probably good to answer here. Reuse seems pretty anticlimactic to use for irrigation, reinjection or dust suppression. Why not use as drinking water? It seems that this system has application point for use treatment at drinking water wells. Well, absolutely.
Yeah.
I guess what we're referring to here is at this site, that's all we can use this water for. But whereas there's other sites we're looking at, which is to do exactly that, is to put a SAFF system in that water treatment plant before it goes into the general population for drinking water.
Yeah, these are the sort of things we're discovering, I guess, mate, is the SAFF technology. We've sort of tested it to some fairly low levels, like 0.1 microgram per litre. We're still being able to pull out the PFAS contaminant from the water. Certainly you could have 10,000 parts per billion micrograms per litre. It'll still work just as effectively as we mentioned at the start of the presentation. That's the beauty of SAFF, is that it still works whether it's incredibly low or incredibly high concentrations. So we've been looking at all sorts of applications in leachate from landfills. We've been looking at it for treating drinking water and floating out PFAS contaminants from drinking water, because that is emerging as an issue. We've looked at construction sites, effectively anywhere where
Surface
you get
drains.
Surface drains are a big one where we've been looking at lately, about putting interception traps into surface drains to do a preliminary cut of the water running off the sites, so that we can capture the majority of the PFAS before it exits the site.
Hopefully, Clint, that it's not quite as anticlimactic as you.
Yeah, there's lots you can do with it. I mean, this
absolutely.
is we were fortunate enough to get one, this large job up at Oakey, which had a particular application adjacent to a source zone, where we would still maintain that's a really good application for this kind of technology. But there's a raft of other applications you can apply it to.
I know there was one we're looking at where you've got an island which has got a water lens underneath it. So we're looking at an option of treating the water in situ, and also as it's pumped out, of putting a SAFF there to treat it before it goes into.
I mean, where we first started on this whole foam fractionation journey was downhole. So we were looking at in-well fractionation capabilities. Our first patent was a downhole foam fractionation process, and that uses recirculating wells interconnected through their zones of influence to almost act as a permeable reactive barrier to PFAS contaminated groundwater that's passing by those well arrays. And so we had some amazing results up at one of the other defence sites in a relatively sandy aquifer. We started with
620 ppb of PFAS, and after 30 minutes of aeration, we'd removed 130,000 ppb of PFAS, leaving 110 ppb in the bottom of the groundwater annulus.
So I mean, the reason why we were still left with PFAS in the bottom of the annulus is a recharging environment. The water's getting treated, the contaminated water flows into the well, and on it goes. And so you can imagine if you had consecutive arrays of wells on the downhill gradient of a contaminated site, you could actually use it very much as a permeable reactive barrier approach.
So just some of the safety things that keep the questions coming. There's some good ones here, and we're just about getting to the Q&A side of things. But I just did want to ask the question of what have we done at Oakey to ensure we've developed a safe processing?
Well, look, even long before Oakey, safety came up. This is OPEC as a company, we dig up bombs, we treat chemical weapons sites, we build huge fuel systems, so safety's kind of in our DNA, really. So right at the beginning of the journey, anyone who was working in the PFAS space, we did baseline blood testing. We wanted to just ensure that our people were safe and that the community was safe. So we have tested down in the laboratory where we're doing aerosol testing adjacent to our PFAS chambers, just to see if there's any aerosolized or volatilized PFAS getting out of those systems. They're all closed and sealed. The containers themselves are sealed, and the exhaust fans on those pass through carbon filters. The knockout drums that we use, the venting on those passes through carbon filters. The tools we use, and this is more from an operational / safety perspective, so we actually have designated zones on the plant where tools are not to go outside of, because again, if you're dealing with parts per billion and parts per trillion contamination, and you take a dirty tool and you put it into a clean zone, you can very quickly contaminate some clean water above the guidelines. And so we actually have colour-coded designated areas. We have PPE that guys can only use in certain areas. So we really do take that safety side of things seriously.
And I think it's come from, as you say, OPEC is one of those very safety conscious companies, and dealing with all sorts of hazardous materials. So we're going to come to some of the question and answers. So I have sort of been picking these as they've come in, but so hopefully I don't miss any. Amy has asked, do you wind up getting any PFAS foaming / removal during the metals precipitation phase?
A little bit. So we have an oxidation tank that sets us up for the plug flow reactor, and you do get some very minor foaming. I mean, it's not quite as easy any bubbles in water create foam. Like you actually, it's a lot of it has to do with the hydrodynamic environment you create inside the reactor vessel. So we try to use the right size bubbles at the right veracity introduced at the right point inside the column, and then we really get this optimized foam. Also, if you don't harvest it fairly quickly, it just collapses straight back into the tank. So at that stage, because we know we've got the fractionator coming up, we don't actually worry about taking that PFAS foam out. But yeah, there is a little bit of foaming.
Okay, hopefully that answers your question, Amy. Christine has asked, what is the recovery rate? I think we've actually shown some pretty...
Yeah, look, hopefully we covered that in subsequent parts of the video, but the recovery rate effectively is we're recovering 100% of PFAS and we're treating 100% of water for discharge.
We could put that table back up.
Yeah, if we want to just pop that back up.
That question.
So those right-hand columns, those right-hand two columns effectively show our trace and ultra-trace testing results post resin. So as we've sort of said, the fractionator is doing the heavy lifting, and at that stage of all of the PFAS, long chains and short chains combined, and bearing in mind at Oakey, this particular signature is a 3M light water material, so it has a certain combination of long chains and short chains, and in that environment we're taking out about 86% of total PFAS after the fractionator, 100% of the long chains, but 86% of total PFAS. And then after the resins, we've removed 100% of all of the PFAS that we're testing for, including the short chains.
Yeah, and under our contract, the two laboratories that do the testing, ALS and Eurofins, are typically testing between 30 to 35 target PFAS compounds.
Yep.
To the detection limits that are on that slide.
Mm-hmm.
Okay, Christine has asked, what is the concentration of inorganic anions? Anions. You can see I'm the accountant in the room. Anions in the hyperconcentrate.
You're the chemist, Dave. You take that.
I can't remember. We'll have to take that one on notice and get back.
Yeah, I mean, it's not a criteria that we're really testing
measured.
for because we're not held to
I think
account
we've
on
done like a test way back. We have characterised the concentrate that we've collected after the hyperconcentrator has made that solution. So we know that there's approximately 12 to 13 ppm of PFAS in there. And after about 6-7 million litres of water that we treated, there's less than 100 litres of that solution in that drum.
Okay, so we've taken on notice and we're going to send it back. So, Christine, if it's all right, we'll send you an email.
Handball that one for a minute.
Yeah, a little bit of information further down the track. So we've covered Amy's 90% question. So Mitchell has asked, what would be the approximate footprint of the foam fractionation equipment for a flow of 2 million litres per day? Could the concentrator tanks be scaled up to handle more flow?
Yeah, great question. So there's really, from our observations and our efforts to date, there's really kind of no upper limit to the size of a fractionator vessel. I mean, imagine a wheat silo or a grain silo properly configured and engineered could be used as a fractionation vessel. So, you know, you could have tens upon tens of thousands of gallons worth of water being treated in a large enough vessel. And I don't believe that there is actually an upper limit. In terms of the footprint, I mean, if we take Oakey, one 40-foot container fits 5 fractionator vessels with a 50-minute cycle time on each fractionator vessel, and that's treating 250,000 litres a day. So in principle, if you were to keep the same residence time, that 50 minutes, you would be looking at a system that's about 10 times that size, 8 times that size, I should say. But what we are finding is, if we look at the degradation curves, a lot of the work is being done in the first 10, 15 to 20 minutes.
25, I think.
And so we're able to really reduce that time by at least half. So you might be looking at 4 40-foot containers for a 2 million litre facility that could be stacked 2 by 2. So you could have a footprint of about, 12 metres long, so say 40 foot by 20 foot wide. If you really want to, if space is an issue, you can compact it right in. I mean, the Oakey plant in many ways for us was a prototype. I mean, we had the luxury of space and we took it. But in reality, a lot of the engineering work we've done subsequently, we realise these systems aren't really going to, the opportunities aren't going to come up on our doorstep. We're going to have to ship them to site. So containerising and modularising the packages that we send has become a really important part of our latest engineering effort.
And I seem to recall we found that the squatter, the fractionation chamber, the better it was at removing the long chain PFAS. So that was a sort of, not a limitation, but the height of the 40-foot container, and optimally that height worked well for us.
It did, yeah. So you've got a 2.4, 8-foot-ish sort of clearance in a 40-foot container. We take up a bit of space with a bund. Those containers are bunded in the base. But it would seem that the narrower and higher the vessel, the more effective they are moving down the shorter chain PFAS removal. And so you'll still get the long chains in a narrow, high vessel, but you'll get better results for the short chains. And the reason for that is because you've got longer residence time of the bubble floating up the column, and so it gets a chance to do more work in the column. So we have in fact worked on 3.5, 4 metre high systems that were quite narrow, and so we are playing with different configurations of columns.
So you could have a combination of columns.
You could have, you could do the heavy lifting with a short squat one that takes out all the long chains, and then move to taller, narrower columns that are focused on short chains. And we're working with a number of unis in Australia, with Macquarie, Uni New South Wales, Monash, and a couple of other guys to look at amendments that are going to improve not just our long chain performance, bring that curve down quicker, but also drive us further down into the short chains. So we're removing more short chains with the fractionator, doing more heavy lifting with just air bubbles, so that we're able to then put less load on our resins. I mean, we're not here to bag resins out. Like, the resins are invaluable. We have to have those as part of the process, but we see them as a polishing phase.
And they're a great fail-safe step.
Yeah.
There's a couple of questions further down which talk about resins. So Anna has asked, hi, would a complex nutrient-rich N-P, which is, I presume, nitrogen and phosphate, and TOC-rich water be a problem?
Not for the fractionator.
No.
Like, there have been other people that have had 40% raw sewage in water contaminated with PFAS at Brisbane Airport. Remediate the PFAS out of that stream, and I think they put millions of litres through it over 9 months, and it's worked.
Yeah,
but they had a polishing treatment afterwards as well.
Yeah, I mean, I guess the value of fractionation is it's as fancy as we'd like to make it, and there are some nuances to it. It is just air bubbles in a column, and so it's quite robust. It's quite versatile in terms of contamination and sediment load and organic load in the water. The fractionation works well. It doesn't like defoaming agents, because obviously foaming is a really important part of the process. So if you've got defoaming agents introduced, that impacts it negatively. So you want to stay away from that. But in terms of water, we've taken some pretty manky stuff, some fairly contaminated waters, and tried to treat them, and treated them very successfully for PFAS removal.
And I guess at the end of the day, PFAS wants to foam when it's in water, so we're just helping it do that.
Okay. Amy has asked, have you done a cost comparison between using SAFF with resin polishing versus just a resin polishing alone?
To some extent we have. I mean, we've obviously, as a company, we're focused on the combination rather than doing resins in isolation. So probably some of the other good companies who work with resins would be able to give you better results for just a cost for resin only. But what we can say is if a SAFF is taking out sort of 80 to 90% of your overall detectable PFAS compounds, and all you're doing is using the energy to drive a pump, and that same pump then generates the air that drives that feeds the venturis, there's no resistance, there's no absorbent medium to push through, and so your energy consumption is very low through that fractionation phase. Your consumables are zero, your waste is zero. So you're really, 3.5 litres is fairly nominal.
I think it comes back down to the concentration of the water you're treating as
Yes,
well.
one of the key things is that SAFF does the heaviest lifting if you locate it up gradient into the source zone. So it's not just pumping water. The water that it's pumping has much higher levels of PFAS in the water to be removed.
Yeah, it's what you guys said at the start of the thing, is that regardless of the concentration, the cost stays the same, whereas that won't be the same for an absorbent water treatment plant, so using GAC or ionised resin.
And where the compound strength of that system comes is that when you get up into the source zone, that's where the long chains are, and that's the long chains that are most important to be removed from the environment and from coming in contact with people.
So just to explain that a little bit further for the guys, I mean, what we've observed across a number of sites, and there's a number of studies that verify this, is that the short chains migrate and move through the environment, through the subsurface conditions more quickly than the long chains do. So what we find is a higher concentration of long chains closer to the source zone and more short chains further away. So we've kind of tried to articulate that the value of the fractionation is its ability to remove all of the long chains. So ergo, the closer you get to source zones, the more effective it becomes.
So you could have a SAFF-only plant right up in the source area, and then you might have either a SAFF plus resin or a resin-only plant down on the boundary of a site that's a kilometre or more away.
It actually brings me to a philosophical argument, which I always like to bring up, but if there's any regulators in the audience, like for us guys out there making these systems, it's really important to know what you want to chase. And so in Australia, for example, where those 3 long chain compounds of PFOS, PFAR and PFHXS are the only things really where we're required under contract to chase, we could just get away with a SAFF only system. And in many environments that may be the case. What we've taken is a precautionary principle by incorporating all of the pre-treatment and resin phases, because we didn't know where in the world these were going to end up, and we didn't know what sort of regulatory environment they were going to end up in, and what the compounds that we had to chase were. So we basically tried to build a system that could manage it all. But if you wanted a system that just dealt with long chains, you could just use SAFF, and you would get 100% of those out with no use of consumables and very little generation of waste.
And pretty low capex.
At a very low capex, like under a third of the cost of a standard plant.
Yeah. Okay. Just if you've got questions, I know people are probably running out of steam, but if you've got questions, log them. We'll be here while there's still questions coming in. Clint has come back and asked, what is I presume it's the same Clint, what is disposal or destruction action for the final concentrate?
So Clint, at the moment we use plasma arc. We haven't had to do it because we've only generated a tiny amount in the last 7 or 8 months. So we actually haven't gone to the destruction phase yet, but our intention at the moment is to use plasma arc. There's a plant in Queensland where we're working, and it's not too hard to get to. What we are working with is 3 different organisations who are developing some destruction technologies where we can manage that hyperconcentrate and destroy it on site. So some of these defluoro technologies and cold plasma, we're looking at trying to have a system, because we've got such small volumes of it. Typically the systems I've seen that are used for PFAS destruction, the limitation is the volumes. If you're dealing with unprocessed water, you just can't get to the 250,000 litres a day or whatever it is. But when we neatly distill it down to 3.5 litres, all of a sudden these technologies become quite viable from a destruction perspective. And so we're really encouraged third-party contractors to work with us up at Oakey. We've sought permission from Defence to allow those organisations to work with us on site. And that's been granted in most instances, and we're able to actually, and we're working towards trying to come up with a closed loop destruction system so no waste actually leaves the site.
Yeah. And I guess specifically what we are seeking to do is to work out how far we take that dewatering stage of the foam concentrate to find the sweet spot for that to go into the destruction cells that are being developed. So at the moment we don't know how far to take it. And I don't believe the destruction cell developers know what is the optimum concentration of foam waste that we can produce that works best in their cell. So we have to come together and determine what that is. So we're...
It might be 500,000 parts per million. It might be 1 million parts per billion. It's, you know, we've just got to...
So it could be in the future that we don't use the drum dryer because that's too concentrated for the on-site destruction cell to work.
Yeah.
So Mitchell's come up with replacement surfactants.
Yep.
Starting to get regulatory traction for remediation. These are come on guys, help me out here. Perfluoropolyethers.
Right. Yep.
Any thoughts on the application of this technology for PFPES?
Yes, we have, and I'm glad it came up. So we've just actually completed a trial on some of the alternative surfactants that are being used, and also some of the low fluorine compounds that are being used to replace traditional firefighting foams. I mean, these are still foaming agents, and fractionation works brilliantly on them. In fact, if you get them from some of these deluge areas, so we're capturing the runoff from some of the hangars on some of the airports and aviation bases, and so that water, which has got lovely, neat, fresh concentrate in it, we can foam that out really effectively. So that's part of the beauty of fractionation, is not only does it work for your legacy contaminants, it also works for your new firefighting foams, your fluorine-free foams. It works for, and you know, one of the other really interesting areas that we're exploring is the ability of foam fractionation to assist with the removal of microplastics, and so particularly in these water treatment plant environments, then it has a great application for removing the two problems that these water treatment plants have, which is both the microplastics and the PFAS contamination. And if we can solve that with one technology on this kind of large scale, as we spoke before about a wheat silo or grain silo kind of operation, that would be just a fantastic outcome.
I might just put one caveat on that, or qualifying statement, is that in some new firefighting foam formulations, if there's new PFAS compounds in the formulation that the labs don't test for, then we won't know whether or not foam fractionation or even resins does or does not remove it.
Fair point.
Because it's all based on what the current contract labs are able to report.
So, you know, you're out to 4,500 PFAS compounds. We typically test for about 35. We're getting great results on those 35, but there's a long way to go. I know some of the guys in the US, in Colorado particularly, are working on expanding that portfolio of products.
I think your point before, Pete, about with some of the new products, it's about good designed fire training systems now, where we're actually incorporating that ability to recycle the water, remove the nasties, and use them again on that fire training facility.
Yeah, look, one of the things that I envisage is that on those fire training areas now, where typically they've sort of run off the apron and the whatever the product is has disappeared into the environment, you're going to see more of a first flush retention system style of design, like you get at service stations, where the runoff from those sites is captured and put back through a plant, and that's where I think foam fractionation plants, SAFF plants, are going to have a great application. They're going to do the fire training exercise, that'll all get washed down into drains, it'll get captured, it'll be returned to a sort of a central holding vessel. We'll be able to strip all of that contamination out and reuse that water for subsequent fire training efforts.
Which is, and it's about just getting involved in that design process.
Yeah, we're just kind of like, we look everywhere we look, we go, well, there's
opportunity,
all these opportunities that it's got to, you know.
Well, we've come to the end of the questions. I think Anna did come back, but I think she was just agreeing with some of the stuff that you guys had said on the couch. So that's good. Just if you're still watching us there, just a reminder, there will be a webinar 3 in the new year. Pete, what's a little teaser?
Yeah, mate. So some of these value add applications for fractionation, working on other in situ applications for it, on other ex situ applications for it. We want to combine those into a webinar. We're working on some really cool technologies and cool systems, if you like, for applying the foam fractionation technology to managing runoff water from causeways, to looking at in-well solutions and how they might work. So the webinar, which will be in the early new year now, will cover off on those areas. So I would say in the interim, guys, if any of you have any questions, like, you know, we'd love to answer them. We want to start to have a voice in that US market. We've been fairly quietly sitting here in Australia developing our own solutions and building our plant and getting it commissioned, but we've got some really robust data now. I should say that the data's not ours. A lot of it is generated by our environmental consultant, WSP, who's contracted by Defence, by GHD, who's our project manager contract administrator on the site. So the data is independent. It's very robust, and a very compelling story is evolving on just how well this can work as part of the treatment train. So we don't see ourselves as the be-all and end-all solution, but we really want to be part of that conversation so we can be part of what is the ultimate treatment train for this
I would
problem.
clarify that, saying North American, we don't want to exclude our Canadian viewers from
if we got any Canadians,
that, opportunity. There is a website if you want to go and send us some emails. It's not a website, sorry, an email address. So if you've got further queries, please go to enviro@opecsystems.com and send them through there. You will get a copy of this webinar. It's been recorded and will be sent to you shortly. You'll also get a survey. We'd really value, if you've got the time, just to quickly complete that survey. It just gives us some feedback as to how we improve the actual presentation, but also, more importantly, the content of these webinars. So I'd like to take this opportunity to say thank you very much for your time. Very much appreciate you joining us. Pete, I'd like to say thank you to you. And Dave, thank you to you.
Yeah, thanks, Connor.
And we'll see you at webinar 3.
Thanks very much, guys. Have
Bye,
a good
everybody.
day. Bye.